A question that some of you might have asked, or maybe haven't asked, is where do we get our hydrogen from? Because molecular hydrogen, if it was just in the air, it is lighter than the other things that make up the air, so it would just float to the top of the atmosphere. So how would we get it? Well, this reaction right over here is actually one of the most cost-effective ways of getting molecular hydrogen, which you can see right over here on the right. What you do at a very high temperature, or what I would consider a high temperature, roughly between 700 and 1,000 degrees Celsius, you get some methane gas in the presence of water. And of course, water at that temperature is going to be a gas. We're talking about steam. And then they will react to produce carbon monoxide and molecular hydrogen. Now, something might be feeling a little off when I wrote this reaction like this. So pause this video and think about what is off here. And I'll give you a little bit of a hint. Think about what are we inputting? What are the atoms and the number of atoms that we're inputting into the reaction? And then what are the number and the types of atoms that we are outputting? For example, we have one carbon that we are inputting between the methane and the water, and we have one carbon that we are getting out on the other side. Think about that for the oxygen and the hydrogens and see whether it all makes sense. All right, now let's work through this together. And actually, to help us visualize, instead of just writing it in this form, I'm also going to try to visualize the various molecules. So this right over here is a methane molecule. You have one carbon that is bonded to 4 hydrogens. You can see that up there, CH4, CH4. Here we have a water molecule. You have an oxygen that is bonded to 2 hydrogens. And then they react. You get a carbon monoxide molecule, or at least how I've visualized it. So you have a carbon and an oxygen. And then I draw the molecular hydrogen. Molecular hydrogen has 2 hydrogens bonded to each other, and that is what I have depicted here. Now, based on the hint I gave you before I asked you to pause the video, you would notice that we have a carbon on the input side. You have it right there. And we have one carbon on the output side. So that seems to obey conservation of mass. Now, what about for the oxygens? Well, we have one oxygen between the methane and the water that we're inputting into the reaction, and we have it drawn right over here. And then we have one oxygen that we are outputting on the output side of our reaction right over here. Now, what about the hydrogens? Well, on the left side of our reaction right over here, we have 4 hydrogens plus another 2, or 6 hydrogens. You can also count them here. 1, 2, 3, 4, 5, 6 hydrogens. Well, on the right-hand side, we only have 2 hydrogens, and they're in one hydrogen molecule. So what happened to the other 4 hydrogens? They can't just disappear. We have to have conservation of mass. So we need to have another 4 hydrogens on the right-hand side of this equation. Well, how can we have another 4 hydrogens? Well, that's if we have 2 more molecules of hydrogen. So that's 1, and then that is 2. So instead of just having one molecule of molecular hydrogen that has 2 hydrogen atoms in it, we now have 3. So to balance this chemical equation, all we have to do is say, okay, we don't just have 1 molecule of hydrogen here. We have 3 molecules of hydrogen. And what I have just done is balance the chemical equation. It's just making sure that we have a conservation of mass, that we don't have constituent atoms on the left-hand side that somehow disappear on the right-hand side, or we don't have constituent atoms that somehow appear on the right-hand side without ever being input into the reaction.